So we're going to talk about branch prediction, but there's one question one of your fellow students asked. Did there ever exist an architecture that required the compiler to supply all information about what are the dependencies, who uses which location, blah, blah, or at least have the processor store information about the dependencies? Because if you run some program frequently again and again, potentially for months, this does seem quite inefficient to have the hardware analyze the program again and again. May be interesting for servers and high performance simulation clusters. May also reduce hardware complexity too, at the cost of compiler programmer having headaches. So this is an excellent question, I think. So first of all, yes, people have designed processors that actually, where the compiler communicate all of the dependency information to the hardware, and we're going to study those in a couple of weeks. Actually, maybe after the branch prediction lecture. It may be actually next Friday, assuming we actually finish the branch prediction by that time. Basically, yes, this is called very long instruction word architectures, and the idea is over there, compiler specifies all the dependencies, compiler knows the structure of the pipeline, it schedules all the instructions, hardware does nothing. So all of this complexity goes away, and you can exploit the benefits of the compiler, you can dynamically recompile, etc. So this is actually a good idea to explore, but unfortunately, it doesn't work in all cases because it's very difficult to extract that sort of parallelism at the compiler. Now, there's another aspect to this question, but we will analyze this in more detail in the next lecture. As a result, as you can see, none of the architectures today are that way. Out-of-order execution is really the dominant architecture because it can fix. But of course, it's inefficient, as your colleague also sees. Every time a program runs, you're doing this again and again and again and again and again, basically. It's a waste of energy if you think about the broader picture, right? You may be running the same program tens of thousands of times, maybe not with the same inputs. So input sets change. So that may change the scheduling of the instructions clearly, but maybe there are some things you can exploit, right? Can you actually recompile the program internally and store it somewhere and run that recompiled, improved version? And that's actually a good idea, I think. That's unfortunately not done as much as it should be, in my opinion, today. Can you actually learn from past executions of a program, and the next execution can be much faster and much faster and much faster? So here, I think dynamic binary translators that can be supported by hardware as well as the software have a big role. If you actually have a system, hardware and software co-design system, where you have a dynamic binary translator, code optimizer, you can actually store that information over time. When your program runs next time, it may be faster. When your program runs the third time, it may be even faster. And you don't need to do a lot of the scheduling in hardware potentially. But this requires more support from the hardware as well as the software stack. So there are a lot of good things in your question. Thank you for asking it. But we will see more of that in the next lecture. Any other questions? Okay, now let's jump into branch prediction, which is a critical component of today's processors. So out-of-order superscale execution, we put a lot of effort into this. We have 600 entry instruction windows. If a branch gets mispredicted, all of those 600 instructions are useless, basically. Think about that. And this has huge impact on performance. And we will see that impact in a little bit. Okay, so as I said, McFarling's Combining Branch Predictors technical report is a very good reading that I would recommend. So these are topics that are not covered by your books. So we're in that territory right now. Your books do not cover these topics much. Okay, recall the slide, actually, we covered the slides, so I'll go through it relatively quickly, but we're going to talk about control dependence. What should the fetch PC be in the next cycle, basically? Answer clearly the address of the next instruction, but it was that address, basically. All instructions are control dependent on previous ones because all instructions change the PC. Some of them just increment the PC by the instruction size. Some of them basically change the PC completely, right? So if the fetch instruction is a not control flow instruction, non-control flow instruction, next fetch PC is the address of the next sequential instruction. So in MIPS, because instructions are fixed size, every instruction is 4 bytes, PC gets incremented by PC plus 4, and that's your next fetch program counter, right? But some instructions at architectures are not that easy, meaning instructions are not fixed size. They're variable sized. For example, in x86, an instruction can be 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, 6 bytes, 7 bytes, 8 bytes, ... up to 15 bytes. Until you decode the instruction, you do not know the size of the instruction. Now, this causes an immediate problem in the pipeline, right? It's not even a branch instruction. It's just a regular instruction. I mean, you don't even know. Whenever you fetch an instruction, you don't know what that instruction is, right? You just know the PC, you access memory, you get the raw bytes. You haven't decoded it yet, so you don't even know it's a branch. Fine, but you don't even know the length of the instruction because the ISA doesn't tell you the length. You have to decode the instruction to get the length. So then what do you fetch next? What should you, by how much should you increment your PC for the next instruction to fetch in the next cycle? And next cycle is not next cycle if you're superscalar. If you're superscalar, next cycle is this cycle. So superscalar complicates the branch prediction also. You control depends even more, right? So existing processes do all of this today, basically. So the complexity, although people have actually put a lot of effort to solve these questions for sure. But basically, if your ISA is not nice, you immediately have a fetch bubble, what's called, or you need to predict the size of the instruction. And this also happens actually in x86 process. You predict the size of the instruction and do the decoding based on that. We're not going to get into that. Okay, but that's another example of control dependence. You're dependent on the instruction side. Even if you're not dependent on, even if you're the next sequential instruction, you don't know the address of the next sequential instruction basically. Even if it's a branch, if it's not a branch instruction, you don't know the address of the next sequential instruction before you decode the previous instruction. But of course, if you know the size of the fetched instruction, it's easy to determine the next instruction address if the instruction is not a control flow instruction. But if the fetched instruction is a control flow instruction, the problem becomes even worse. Basically, how do you determine the next fetch PC in this particular case? In fact, how do you even know whether or not the fetched instruction is a control flow instruction? You do not know this information until you decode the instruction as well. Okay, you can predict again. And we're going to see that we're going to predict, basically. So there's a lot of complexity in the fetch engine, basically. This is part of the von Neumann complexity, basically. You're fetching instructions and you need to do a sequential fetch. This causes branch prediction problems. Actually, data flow process reduce this a little bit if at the ISA level, but they add complexity in other parts of the engine, clearly. Think about that for your own benefit. Okay, so we're not going to tackle the instruction size problem. We're going to assume fixed size instructions, but we're going to tackle the branch control flow instruction problem. What is the next PC and how do you determine that? Next fetch PC and how do you determine that? So for this you need to recall the branch types also. So there are different branches, conditional branches, unconditional branches, calls, returns, and indirect branches. And this is a classification of the branches. And the key is different branch types can be handled differently. We're going to focus a lot on conditional branches. Direction is not known, basically, at the fetch time. You do not know which direction, taken or not taken. And there are two possible next fetch addresses, which is PC plus 4 in MIPS, or the target address of the branch. And the fetch address is resolved when you execute the branch, meaning it's register dependent. So fetch address is resolved down at the later parts of the pipeline. In an out-of-order engine, whenever the register becomes available, basically. Unconditional branches are easier to handle because they're always taken, and there's only one possible next fetch address, and it's handled and decoded in this part in MIPS, for example. Calls and returns enable function calls. We're not going to discuss them in detail, but it's good to know that they're handled separately in existing processors. But they also break the control flow. Calls are always taken, and the target address is determined in decode. Returns are always taken, but the target address can be many, not just one, because there may be, you may jump to a function from many different call sites. And when you return from that function, you should be able to go back to the place, to the call site that initiated the function, right? So there may be 1,000 places in the program that call the same function. Whenever you return, you need to go to the right one of those 1,000 call sites. How do you do that? This happens by communication on the stack. Whenever a call instruction happens, it pushes the next fetch PC, next program counter, PC plus 4 on the stack. And whenever the return happens, it pops the stack and gets the program counter that it needs to jump to, basically. That's why the number of possible next fetches is many, and this is execution based. That's why you know the return address. So existing processors actually employ what's called a hardware call return stack to mimic what the software is doing to accelerate call return predictions. Basically, whenever you fetch a call instruction, you figure out the target address, you decode it, and then you put it on a stack, hardware stack. And then you keep doing other calls, you basically put them on the stack. If your returns are balanced with the calls, meaning returns are matching with the calls, and in a nice program, the nesting level of the call should match the nesting level of the return. Actually, the other way around, the nesting level of the return should match the nesting level of the call, unless you're using weird control flow constructs like gotos. How many people here use gotos? How many people are aware of gotos? Okay, good. How many people use them? Okay, good. If you know why you should not use them, you should probably read Dijkstra's seminal paper on goto considered harmful. So basically, Go-tos enable you to jump any point in the program, but it's very irregular structure, right? Calls and returns are very methodical, that enable you to match the nesting level. And existing hardware behaves that way also, basically. You fetch a return instruction, you look at the top of the stack and say, oh, in the call return stack, this is where I should jump. So you pop the program counter over there, and you basically, that's your next fetch PC in that case. But of course, how do you know that's a return instruction? That's another problem, right? Whenever you fetch the instruction, you don't know if it's a return instruction. You need to decode it. So you may need to have one bubble to be able to do that, or you need to predict that it's a return instruction. Okay, indirect branches are actually very interesting also, because indirect means they're always taken. There are many possible addresses, and the address is in the register. So this is useful for example, implementing virtual function calls. People here know about virtual function calls, I assume? No? Case switch statements, you know about those? Okay, good. So virtual function calls are actually, let's say, extended case switch statement. This is it's a function of object-oriented programming. You may have one object, and basically when you program, you call objects area function, right? But you don't know the object when you program. Object can be different things. It could be a square, it could be a circle, it could be a rhombus, I don't know. It could be a trapezoid. And these all have different functions. The object is dynamically determined based on the input, and the virtual function call, basically you jump to the right function call that's to be executed based on the type of the object. So that's called a virtual function call. Basically, you jump to a function call depending on the type of the object that's determined dynamically, and that's why you need a register to decide where to jump to. That's the virtual function calls are translated to indirect branches. Case switch statements are kind of similar also. You basically have a case, you basically have a switch and you have a case, and depending on the input to the switch statement, you go to a different part of the case statement, right? Different case statements. And these could be implemented as different function calls. And people use indirect branches. Well, not necessarily different function calls, but people use indirect branches to determine where to jump to based on the case, based on the switch. So indirect branches are interesting because they have many targets. They're always taken, and they're execution based, and you have no idea where to jump to. In returns, you kind of have an idea. If the program is well structured, you should be jumping to the top of the stack, right? The address on the top of the stack. But indirect function calls are even harder. If you have time, we'll talk about that, but we probably won't have time. So keep in mind that existing systems, existing processors actually have different branch prediction methods for all of these. We're going to focus a lot on the conditional branches. If you have time, we'll talk about the others also, but probably won't have time. I'll point you to slides and lectures. The interesting thing is there's no conditional indirect. That would be the hardest, right? Indirect branches are always taken. They're not conditional. If you had conditional indirect, then that would be a harder branch type. As far as I know, no ISA has conditional indirect because you don't need it. I think you can combine them separate. Okay, so basically there are specialized mechanisms for handling branches in existing processes because this is so important. Okay, so how do we handle control dependence? Clearly, it's critical to keep the pipeline full with correct sequence of dynamic instructions. There are many potential solutions. Just like data dependence handling, control dependence handling has many solutions. Stall the pipeline. Bad idea. We'll cover it very quickly, but hopefully this is already clear that it's a bad idea, right? Until you know the next fetch address. Okay, guess the next fetch address. We've kind of seen an example of this. Next fetch address is the next sequential instruction. This is called branch prediction. We're going to see much more sophisticated methods, including machine learning methods in this lecture. Employ trade branching. Basically change the semantics of the branch instruction. Branch instruction doesn't take effect right now. Branch instruction says, oh, you should execute the next 3 instructions after me and then branch. Or you should wait 10 cycles and then branch. This is a bad idea, as we will see also, because it ties the branch instruction semantics to the microarchitecture and vice versa. So hopefully we'll have time to talk about that in the next lecture. Fine-grained multi-threading, our friend, applies here also. Do something else. I don't want to deal with this branch. Well, I don't want to deal with any dependence, and I have enough threads, so I don't have the branch problem, right? As we discussed, fine-grained multi-threading is beautiful if you don't care about the performance of this thread. And yeah, there are 2 other interesting directions which we probably won't have time to talk about. I will actually mention a couple of these with respect to something else, but you can try to eliminate the control flow instructions as much as possible. Get rid of the control flow instructions. This is called predicate execution. Turn the control flow to data flow, basically. So as opposed to having a control dependency, introduce a data dependency. And this, again, data flow-based principles. And you can easily do that basically in most branches, not all branches. Loop branches are a bit harder to do. But if and else branch, right? You can turn that into a predicated execution where you fetch both parts in the code, but the execution of one of them is dependent on the value that you produce, basically based on the predicate. So if the predicate is false, that thing that you fetched is not going to execute. If the predicate is true, that thing you fetched is going to execute. I'm not going to go into a lot of detail, but this is the key idea. And compilers can actually do this. And this way, you don't have a problem immediately at the beginning of the pipeline. You have a data flow problem right now. The data dependencies are increased, control dependencies reduced. So you're basically making the trade-off that I don't want to deal with the control dependencies. I want to turn it into a data dependence and handle it just like other data dependencies that I'm handling in my auto-word range, which is not a bad idea, actually. Of course, it doesn't buy a whole lot of performance because there are many other reasons why you cannot employ it, because not all branches are very simple, basically. Okay, the other idea is fetch from both possible paths. This is a bit different from predicate execution, but whenever you get to a fork, a branch is a fork, right? You go here this way or this way, a conditional branch. Take both paths, execute both. Eventually, you'll figure out which path is the correct one and flush the path that you don't want. This is called multipath execution. It becomes very costly because paths become exponential, right? Okay, you took the fork here, and you saw another fork here. You took the fork over there, and you saw another fork here. You took the fork. You saw another fork. You took the fork. Now you see that there are exponential number of paths, 2 to the n, based on the frequency of the branches that you encounter in the program, and only one of them is correct. So basically, you're filling the machine with many, many different paths, control flow paths. Only one control flow path is correct over there, because only one. That's the nature of a von Neumann program. Okay, so this is a bad idea if you always do it, but these ideas could be actually very useful if you do it very selectively. Meaning, I have no idea how to predict this branch. It's very, very hard to predict. I have all known methods implemented in my processor, like all of these maybe. I cannot predict it. So let me take 2 paths on this one. I don't do it for every branch. I do it very, very selectively for key branches. Then you may actually win. Okay, so as I said, hopefully we'll have time to cover some of these. I will not have time to cover all of these, but let's talk about stalling the pipeline and dismiss it again. So basically, stall fetch until next PC is known is a good idea. Even if you don't have branches, you stall for 50% of the cycles. Basically, non-control flow and unconditional branch instructions. Because you don't know the instruction, you need to determine the instruction and then change the PC. Basically, 50% of the cycles are wasted. So this is a really bad idea, stalling. You have to do at least next PC, meaning PC plus 4 prediction. Clearly, you get much worse stalling for conditional branch instructions because conditional branch instructions are resolved in the MEP stage, if you remember, from the old pipeline. This is our old pipeline. Okay, let's take a look at do something else, fine-grained multi-threading. You already know what to do over here. Each pipeline stage is an instruction from a different, completely independent thread. As a result, there's no branch prediction problem. That's good. And no need to perform any control and data dependence handling. But you already know that this doesn't work for the performance of this program. So we're going to try to improve the performance of this thread. And it comes at a hardware cost. Okay, so that's why we want to guess the next fetch address. And all machines today do the guess next fetch address part. But let's before we go into different methods of branch prediction, let's try to understand why this is so important. Why have people actually tried to design better branch predictors for decades and decades and decades, and they're still trying to? So let's control flow instructions are actually quite frequent. Depending on the program you write, it could be 15 to 25% of all instructions. And next fetch address after control flow instruction is not determined after n cycles in a pipeline process. N cycles is called I'm going to provide some definitions. This is called the minimum branch resolution latency. And then, okay, something is not happening. Okay, if we're fetching W instructions per cycle, this is superscalar now. W is the width of the superscalar processor. If the pipeline is W wide, branch misprediction leads to n times W wasted instruction slots. So if you mispredict the branch, n times W instruction slots are wasted. You couldn't utilize them. You may have fetched wrong path instructions to all of them, actually. So let's take a look at it. Let's make some assumptions. N is 20, which is similar to today's processors, actually. People have tried to increase it to 30 in the past, 40 in the past. Because of branch issues and data dependency issues, they had to back down a little bit. W, let's say, is about 5. Today's actually we're much higher. We're at 8. So it's going to be amplified. Today's issues are amplified based on what I'm going to discuss here. But 5 is a nice number based on the assumptions that I'm going to show you next. Because I'm going to assume 1 out of 5 instructions is a branch. So assume that each 5 instruction blocks end with a branch. The question is, how long does it take to fetch 500 instructions? So these are the assumptions. So if I give you these assumptions, you should be able to calculate this. Not really, because I didn't give you the accuracy of the branch predictor. So if the accuracy of the branch predictor is 100%, you did not mispredict anything. You're fetching 500 instructions, and you're fetching 5 instructions per cycle. Because you didn't mispredict anything, you should be able to fetch 500 instructions in 100 cycles, right? 500 divided by 5 basically, right? All instructions that you fetched are in the correct path. So you didn't spend any cycles on the wrong path. Okay, so the interesting thing happens. So no wasted work. Clearly, your IPC is 5. That's what you would ideally achieve, assuming no data dependencies, of course, which is not what we're dealing with here. So if your accuracy is 99%, which is a really good accuracy, actually, for branches, now we have 500 instructions. 1 out of 5 is branches, so we have 100 branches. 1 of them is mispredicted. Only 1 is mispredicted in the 500 instructions, meaning that 1 time in the fetch of these 500 instructions, we're going to waste 20 cycles, right? Because n is 20, okay? So 100 cycles, we still need to fetch. We still need to fetch correct path instructions. We still need to fetch 500 correct instructions. So we spend 100 cycles to fetch them, but we also spent 20 cycles on the wrong path, because 1 branch is mispredicted and it's cost us 20 cycles. So now we took 120 cycles to finish the 500 instruction program. We fetched 20% extra instructions, as you can see. And our IPC is 500 divided by 120. Why is it 20%? Because we fetched 120 cycles as opposed to 100 cycles, which is 100% accuracy. So our IPC already went down to almost 4, as you can see, with 99% accuracy. That's a very highly accurate thing. Okay, 90% accuracy, more realistic today. Now you fetch 10 instructions on the, you mispredict 10 branches. Each branch costs you 20 cycles, and you spend 200 cycles on the wrong path, fetching. And 100 cycles on the correct path to fetch 500 instructions. So total time is 300 cycles for this program. And you fetch 200% extra instructions, and your IPC went down to 1.66 as opposed to 5. So even if you're 90% accurate, 90% is pretty good, I would say. In hard programs, you cannot even get 90% today, but 90% on average you can get today. Fine. Even then, you have a problem, as you can see, right? Okay, if you actually go to 60%, life is terrible. Basically, 40 of the branches mispredicted. Each of them cost you 20 cycles. So 900 cycles do you spend for fetching 500 instructions, correct path plus wrong path. Your IPC is less than 1. 5 divided by 9. So 60% accuracy doesn't cut it, basically. If you want to build a deep and wide machine, you'd better be, I don't know, at least 90% accurate. But I would argue that even 90% accuracy doesn't cut it, because you're wasting a lot of power also, right? 200% extra instructions fetched. Does it really make sense to fetch out of every 3 instructions you fetch, 2 instructions is useless, basically. That's what this means. I'm not even going here, right? Out of every 9 instruction I fetch, 8 instructions is useless over here. So that's why branch prediction matters a lot. Okay, that's why we're going to spend, let's say, 1.5 lectures on it. And you know the basic idea, so I'm going to go through the earlier parts relatively quickly. So we want to guess the next instruction to fetch. If you stall fetch, it's a bad idea, as you can see. If you predict, that's good. So, and even in this easy case, you get performance improvement. And you can do these animations by yourself. But you've already seen the next sequential prediction, which is you predict the PC as PC plus 4, next PC as PC plus 4. So these are relatively baby steps, let's say. Of course, branch prediction leads to misprediction penalty when you actually mispredict. So you need to flush the pipeline. And that's what we kind of analyzed in the prior slides. So simplest prediction method is always guess next PC is PC plus 4, right? And we did that in the pipeline we designed in lecture, I think 14. We always predicted the next sequential instruction is the next instruction to be executed. And this is really a form of branch prediction, next fetch address prediction, as we discussed. You can actually make this more effective also. So somehow you try to maximize the chances that next sequential instruction is the next one to be fetched. So remember, you get to a branch. We're going to talk about a branch right now because this is always true if it's not if the instruction is not a branch, right? If the instruction is a branch, you have two possibilities. Next instruction is either at PC +4 or at the target. How do you try to maximize that the next instruction you fetch is actually at PC +4? Well, the compiler somehow figures out how to lay out the code such that the likelihood of the next instruction being in PC +4, address PC +4 is higher. And this can happen if the branches are biased. Basically, software method is to lay out the control flow graph such that the likely next instruction is on the not taken path of the branch. So let's try to do this. Is this turned on? Or how do we turn it on, in other words? Okay. I guess while it's turning on. Can you see it? I don't know, maybe you can help me if it's turned on, I don't know. It's warming up, I guess. It always takes time, but you cannot see it. So if I stop sharing, will you be able to see it? Say it again. Oh, okay, it's connected somehow. Okay, is it this? Okay, okay, that's good. Okay, there's something happening. Okay, I guess. So basically, I'm going to call this A, and then we have a branch, right? And then B, C, and then D. Okay, so this ends as a branch clearly. These are called basic blocks, and this is a control flow graph. I guess each of them is a basic block, and this is a control flow graph. Basically, this branch can go this way or this way. Now, compiler profiles the code that's running. I mean, each of these blocks actually have instructions that end with a branch. Compiler profiles the code and finds out that this is 99%, you go from A to B, right? And at 1% of the time, you go from A to C. I mean, it doesn't need to be, they don't need to converge in D, for example. You can ignore the D. And the compiler lays out the code such that B always comes after A in sequential. So if the branch is at PC, the beginning of B is at PC +4, right? If the compiler knew the frequency of the transitions between edges of this control flow graph of your program, then it can basically lay out the code such that the prediction of next PC equals PC +4 is more effective. Now, if this is the case, if these are the probabilities, it makes no sense to lay out the code such that you have A and then C next, and then branch B is somewhere here, right? Because you know that 99% of the time, you're going to go from A to B, and your prediction method that's employed in your processor, next PC equals PC +4, will fail 90% of the time. So if you have a smart compiler, you can do what I said. Figure out the probabilities of transitions, meaning branch taken or not taken probabilities, and then make the not taken path the probable path. That's the idea. Of course, how does the compiler figure out these probabilities? Well, it needs to profile the code. It needs to profile the code, examine with hopefully representative input sets. If the compiler profiles the code, and this is 99%, and then lays out the code this way, but during real execution of the program, the real frequency happens to be, this is 99%, this program is terrible, right? So that's the importance of the representativeness of the input set problem, meaning whenever the compiler profiles the code, it should get good information that should be representative of what's going to really execute when the program executes. And that's usually a tough problem. So this is nice, clearly, right? You try to make the layout of the code such that next PC equals PC +4 prediction do as well as possible. Of course, this works if the bias of the branches look like this. This looks different. Meaning 99%, 1%, nice. And if it's, of course, representative, 90%, 10% sounds good. If it becomes 50% and 50% this probability, then you have a problem, right? The compiler cannot do anything. And there are many branches that look like that, basically. So it turns out most branches are biased, meaning this you can actually do this optimization nicely. But the harder to predict branches are actually not so biased, 60 to 40, 50 to 50. So this sort of improvement doesn't always help. Okay, so hopefully that was clear. If you have any questions, let me know. So basically, that's the software. Software laying out the code. Nope. So I need to, oh, it automatically switches. Wow. Finally, we have a slightly more intelligent machine here. It doesn't always do that. In the past, it didn't do that. Okay, so, and this is actually employed by many compilers today. This is a beautiful paper that was written by Pettis and Hansen, Profile Guided Code Positioning, in 1990 in PLDI, Programming Language Design and Implementation. And a lot of compilers actually employ this. Now you can do the same thing in hardware also. So let me philosophize a little bit. Whatever you can do in software, you can also do in hardware. The difficulty is at how much cost do you add to the system. So you can do exactly what I described in hardware as well. There are machines that did that. Intel Pentium 4 is one example. What they did was basically, okay, how do I switch back? I guess if I stop sharing, it'll automatically switch back. What do you think? Not new share, stop share. Okay, maybe not. Maybe it doesn't predict intent. Okay. Yeah, basically in the hardware, what you can do is you can try to figure out the probabilities. Whenever you execute the code the first time, you figure out A is always followed by B. I don't know, not all of these pens are good, let's say. You figure out A is always followed by B, and B is always followed by D. D is always followed by F, always meaning 99% of the time. And the hardware, what it can do is, it basically has storage that basically stores A, B, D, F. These are instructions. These are basically basic blocks. There could be 10 instructions here, 12 instructions here, 15 instructions here, 20 instructions here, I don't know. The hardware stores all of these in a sequential order. And it executes these instructions in that order. Basically, fetching right now is seamless, assuming that almost always you go from A to B, B to D, D to F. This is nice, right? You laid out the code in hardware internally in your microarchitecture, so that you don't need to basically, you almost always correctly predict these branches. If there's a misprediction, of course, you need to flush the pipeline and fetch from the right place. So basically, this code layout optimization can be done in both software and hardware. I'm not going to cover the hardware version. I mean, I briefly covered the software version just to give you the idea. But basically, this is the idea of caching traces of executed instructions. Okay, it didn't figure out that I switched. Basically, we're caching the traces of executed instructions. After we execute once, twice, 3 times, 4 times, 5 times, we count. We figure out what fraction of the time the branch was taken, each of the branches. And then we basically figure out a trace of executed instructions in the program and cache them somewhere. And then supply them to the, next time we fetch the instructions, we supply them in that order to the pipeline. And this idea was called trace cache. It was implemented in Intel Pentium 4. It's not simple. It's more expensive, but it does buy some performance. Okay, so even the point of the slide is, even a prediction method like next PC equals PC plus 4 can be enhanced, right, by software or hardware methods. So don't dismiss any idea as bad. If you actually have right support from the software and the hardware, for example, dynamic compiler can actually do this. Maybe hardware can do this. Maybe next PC equals PC plus 4 is not a bad prediction mechanism. Now, the difficulty is these hard to predict branches. What if your prediction accuracy is, what if your branch is not biased? 50%, 50%, 60%, 40%. So this, unfortunately, this idea doesn't work with that. So how else can you make this next PC equals PC plus 4 more effective? Get rid of control flow instructions. Basically, this is what we discussed, or minimize their occurrence. So you can get rid of unnecessary control flow instructions by combining predicates. It's called predicate combining, and testing only once. For example, if you're testing 10 different conditions to execute one piece of code, that may lead to 10 different branches, right? You're testing, for example, if A equals 4, branch or continue. If B equals 5, branch or continue. And then if C equals 10, branch or continue. If N equals greater than 5, branch or continue. As opposed to doing individual branches on each, why don't you combine the predicates, meaning do some data flow, basically compute a value based on the branch conditions. These are called predicates, branch conditions called predicates. Combine them together in a single statement and branch on that statement. As opposed to doing 10 branches, just do one branch. And this is another example of converting the control flow dependence into data flow dependence. You may be doing some extra work, of course, by not terminating the computation chain earlier. So this is one example of making PC equals PC plus 4 more effective, because now you have sequential line of code as opposed to 10 different branches that are branching out. And you can also convert control dependence into data dependencies, as I briefly described predicate execution. If we have time, I'm going to talk about that. But okay, we already know branch always PC plus 4 prediction. You can see that branch condition and target are evaluated in the ALU. And if you actually mispredict, you need to flush the instructions that are coming next. I mean, we've seen this, so that's why I'm going through this relatively quickly. We've already seen actually a lot of the things that I'm going to discuss right now also, which is early resolution of the branches. So let's do some performance analysis. We kind of did this earlier, but assume you have correct guess, no penalty, incorrect guess, only 2 bubbles. And 86% of the time you're correct. And no data dependency related stalls, 20% control flow instructions, and 70% control flow instructions are taken. This is your CPI basically, in a very simple process. You can do this calculation by yourself. Basically, 14% of the instructions cause 2-cycle bubbles. That's what this is basically. Because 30% of the instruction, 30% of the branches are predicted correctly. Meaning only, and branches are 20% of the instructions, as you can see. Okay, so the reason I'm going to point this out is there are 2 equations to branch performance. One is with what probability do you get the prediction correct? In this case, wrong. And what is the penalty for the wrong guess? So we're really guessing whether we're going to take the branch or not take the branch. And there's a penalty associated with it. And both of these are important, actually. You need to optimize for both, actually. If the penalty for a wrong guess is extremely large, even if your probability for a wrong guess is very high, just like we have seen, that probability may not be enough. 90% may not be enough for you, basically, if your penalty is large. If your penalty is small, maybe you can get away with a smaller probability of a correct guess. That's the idea, basically. So you can reduce either of the 2 penalty terms. And we've seen an example of this before, actually. In the pipeline that we have seen in lecture 14, we resolved the branch condition and target address early, right? If you remember, we actually moved replicated the adder and equality checker over here so that we can compute the target address and the BEQ for BEQ and MIPS. And we discussed if it's a good idea. And this is another example that we see. We basically calculate the branch target and condition the decode stage. But it's not necessarily a good idea, and it may not always be possible. Like in an out-of-order execution processor, actually, this is kind of doesn't make sense, right? Can you actually compute it early? With unconditional branches, I mean, actually existing out-of-order processors are very complicated, so they may actually do some things very similar, but it's not easy to do completely. Okay, that's why we're going to see enhanced branch prediction. And enhanced branch prediction has 2 characteristics. One is we want to actually improve the branch predictor accuracy, but we also want to get rid of the bubbles that we have. If we're correct or incorrect, we don't want to have any bubbles in the pipeline. So we're going to be very aggressive. Meaning, what does this mean basically? Predict the next fetch address to be used in the next cycle. We don't want any wasted cycles on correct prediction. Incorrect prediction, we may have wasted cycles. We're going to minimize that as much as possible. But on correct prediction, we don't want to wait at all, right? So this cycle, we're fetching an instruction. We want to know what's the next PC in this cycle. At the end of the cycle, we should latch the next fetch PC to the program counter. Right? So this requires 3 things to be predicted at fetch stage, actually, not just one thing. Whether the fetched instruction is a branch, what is the direction of the conditional branch, and the branch target address, if the branch is going to be predicted taken. Right? So you need to know all these 3 things. So we're going to talk about these 3 things. So actually, 2 of these things can be remembered from past executions of the branch. Basically, target address remains the same for a conditional direct branch across dynamic instances. So this is good to keep in mind. This is true for unconditional branches also. Only for indirect branches and calls and return. Well, this is true for calls also. Indirect branches and returns, this is not true. So basically, the fact that target address remains the same says that if we execute the branch once, we calculate the target address. Why don't we store that target address somewhere in some memory structure? And the next time we see that program counter, we index that memory structure and get the target address. And this tells us 2 things. One is, if we actually get a target address from that memory structure, that tells us that that's the target address for the branch. That also tells us that this is a branch, because I've computed a target address for this PC before. So we kind of kill 2 birds with 1 stone in this case. So that's the idea, basically. Store the target address from previous instance and access it with the PC. This is called a branch target buffer or branch target address cache. So let's take a look at the fetch stage with BTB and direction prediction. So let's start with this direction prediction. So let's assume that you have a direction predictor, whether the branch is taken or not taken. We have a program counter. Clearly, this is the address of the current branch or instruction. You index and there's a cache of target addresses, branch target buffer. You index both with the program counter. Let's take a look at this first. You index cache of target addresses. It returns an entry to you, target address. It also says, oh, I hit, meaning I found an entry for this program counter. And then you also index the program direction predictor concurrently. It tells you whether the branch should be taken or not taken, right? So these are the two major structures that we will see. And if you hit in the branch target buffer, and if the branch is taken, then the next fetch address should be the target address stored in the cache of target addresses, branch target buffer. If you either miss in the branch target buffer, or if the direction predictor tells you not taken, then the next fetch address should be PC plus 4 in MIPS, or PC plus instruction size. Right? So if the instruction size is not known, you can also predict that, right? Instruction size variable, you can also have another structure to predict that. Right? So that's basically the next fetch address predictor we're going to examine this lecture and the next lecture. Hopefully this is clear. Does this make sense? So here we're remembering the target addresses for different PCs. We're associating target addresses we computed for different PCs in prior executions. And here we have some magic. We're going to try to predict whether this conditional branch is predicted taken or not taken. And we're going to look at only conditional branches in these lectures until we switch to some other branches if we can. Okay, so more sophisticated branch direction prediction does something like this. So you basically, branch target buffer gives you the target address if it's present, and a hit signal, hit or miss signal, whether the target address is there. And you can also incorporate which direction earlier branches went. So this actually is going to aid us to predict this direction better. So by knowing which direction some earlier branches in the program went, we're going to make this direction prediction more accurate. And if this sounds like magic, this is not magic, because there's a pattern to execution of different branches. Branches are correlated with each other. And this correlation we're going to exploit so that we can predict the branches much better. So this will improve the accuracy of our branch prediction, of the direction predictor. And the rest remains the same. Okay, so as I said, the third, meaning branch target address prediction, can be accomplished with a BTB. We remember the target address computed last time branch was executed. We know whether the fetch instruction is a branch, again using a BTB. If the BTB provides a target address for the program counter, then that means that it must be a branch, unless you incorrectly updated the BTB, hopefully not. Or you can store branch metadata bits. So there are actually some processors that partially pre-decode the instructions, but I'm not going to talk about that. The key question is the second one, basically. How do you predict the direction of the branch? Is it taken or not taken? How do you reduce this branch to a single bit, basically, taken or not taken? And that's what we're going to cover in the next lecture. So I'm going to stop here. We're going to cover a lot of methods to do branch prediction, direction prediction. Okay, I think we're done. If you have any questions, feel free to come and ask. Otherwise, have a good weekend, and I'll see you next week.